before I introduce Birgir, who is giving today's talk, I just want to say welcome to everybody to our remote sensing lecture series. This is a lecture series that is arranged within the remote sensing center that we are starting to build up. We try to have lecture series in the fall and in the spring. And if people have ideas for future remote sensing lectures, they are very, very welcome to write me. I wrote the web address to our website and my email address, so you can contact me if you have ideas on lectures. Also, if you know that you're not on the remote sensing email list that we have, also just write me and say you would like to be on the list. So this talk will also be recorded and be available after a couple of days when it has been edited. So you can also find that on our website. I will send an email out through our email list later on. Okay, but without further ado, I would like to welcome Birgir Wilhelm Óskarsson from Náttúrufræðistofnun. He's a geologist and he's been very much leading the effort for 3D mapping. And today we'll give a talk called 3D Mapping and Photogeology at the Icelandic Institute of Natural History. So thank you so much, Birgir, for joining. The floor is yours.
Thank you, Gro. I hope you can hear me well. So hello everybody. I will in this talk about the photogrammetry lab at the Icelandic Institute of Natural History. The lab was inaugurated in 2019. Was part of a joint application into the Danish Infrastructure Fund in 2018, where 5 institutes, us, the Icelandic Institute of Natural History, the Earth Science Institute at the university, and ISOR, IMO, Veðurstofan, and Almannavarnir, the civil protection, we got a fund to set up a photogrammetry lab at the Icelandic Institute of Natural History. So the lab has its office here at the lab at the Icelandic Institute Natural History. It's equipped with 2 workstations with good processing power to run relatively large photogrammetry projects. It has also equipped with digital cameras, drones, Trimble high precision GNS instrument, and bays and other accessories for photogrammetry surveys. And what do we do at the moment? Ongoing projects. We have been very much focused on geological mapping projects. We do terrain mapping and also outcrop mapping. Terrain mapping, then we are focused on topographic models or digital terrain models, OTMs, or DTMs, or DSMs. And then outcrop mapping, we're more focused on geological mapping, high resolution, extracting high resolution data out of outcrops, usually vertical, cliff sides, mountain faces, areas that are difficult to visualize from vertical aerial photography. We're also involved with monitoring, and as Jago mentioned, been active in the monitoring of Fagradalsfjall eruption, and I'll come back to that a little bit later. But we have been achieving, near real-time feedback or in the processing of data of that monitoring. We've also been monitoring erosion and sedimentation of Surtsey Island since 2019. I'll show you a few images of that. Mass movements, not so much, but we have mapped. There's potential for mapping these, but we have done some work around landslides and slumps and glaciers and glacial environments. We have not been involved much in these, but there's also lots of data that we have collected that is useful for these purposes. When we photograph mountains in the east and Tröllaskagi, we have also photographed glaciers and the environments around these glaciers. So we have plenty of data that can be used in the future for monitoring these environments. And then we do other things. We have monitoring of natural reserves, touristic areas, and also archaeological sites, and then small scale. We also generate small scale 3D models of objects or specimens, rock specimens, animal specimens, plant specimens, and things like this. Now, just a short overview of what photogrammetry is. Most of you are familiar with it and know what it is, but it's a remote sensing technique for extracting 3D observations from 2D images. As just the name, photo, light, gram, drawing, metry, measurement. So we're drawing surfaces from photographs, images, 2D images, and then prepare them in order so they can be used for measurements and mapping and quantifications. So it's used for science, but also a lot in entertainment business, film industry, gaming, and so the applicability of photogrammetry is very broad. And sensors, then sensors that receive light and not emit light, like LiDAR. These are sensors that receive light. Cameras could be also multispectral cameras, but we work mostly with digital cameras of various types. So we are dealing with digital photogrammetry. So common types of photogrammetry, there's the orbital images when we use images taken from satellites, aerial images taken from crewed aircrafts or manned aerial vehicles, UAVs. But it could also be terrestrial, just taken from the ground, or close range. UAVs can also be used for that purpose when you hover around something very close to the object. Now, cost, and many costs, is visually effective. Using photographs, you see a lot of things in the photograph. It's time effective. You can cover large areas in a very short time. And it's cost effective. Equipment is relatively low cost. You can, for example, use conventional handheld cameras, and they don't have to be expensive. And there are many open source softwares today that allow for photogrammetry or even processing, editing images. So it's very cost effective, and it's also non-destructive and non-invasive. You can take a model with you home, or you can take a terrain or an outcrop with you home, and you're not destroying it. So you take it as it is. Just a quick overview of the workflow. We have field acquisition using digital cameras, and as I mentioned, it could be any camera. Today, technology has advanced so quickly, actually, in this field that you can use almost any camera or cell phones and acquire images, and you can throw them into photogrammetry softwares, and they will generate a model straight away for you. And you can even download apps with these photogrammetry apps that do this from the images in your cell phone, if they're just collected with the purpose of photogrammetry, with overlap and all that. So today the technology is very accessible and easy to use. But if you want to use it for scientific purposes, then you have to think about a few more things. So after acquiring the images, you process the data, and you go through an image alignment and type point generation. And so a relative model is constructed from common points in the overlapping images, which are these type points. And if you then want to move from a relative model to for that model to have an absolute orientation, then you add control points, which with known coordinate system, with known coordinates, or you can use the position of the and orientation of the cameras, and then all this information is weighted in a bundle adjustment, and then you have a model that is scaled or placed in the real world within a coordinate system. And then when you have a type point cloud, you can either export that or import that into stereo softwares that allow you to then see the images you have within a coordinate system, and you can start doing observations straight away in stereo mode by looking at the images in stereo within that background or the coordinate system, or you can process it further and construct dense point clouds, DMs, or mesh models, and ortho images. So for just a short overview of the photogrammetry, of a photogrammetry survey, things you need to have in mind when running a survey. First is photography. How are the images taken? What is the quality of the images? You need to know how to take, let's say, sharp images that are not blurred. Often images are being taken from moving vehicles, aircrafts, drones, and you have to know how to take photographs that are sharp. And other things like overexposure, underexposure can be actually corrected for, so these are not crucial, but the images need to be sharp. Another thing you have to consider is flight planning and image overlap. You need to have image overlap of 70-90% or 20-40% if you have blocks or stripes for the lateral overlap. And it's not a requirement to have a flight planning, but good planning can reduce the number of unnecessary images and speeding the processing time. And when we think about sort of near real-time response, processing time is important. So good flight planning, could be of good use. And it's also important to know the resolution of the images you're looking for to plan the flight with the right distance or altitude from the object you want to photograph. Camera orientation, drones have inertial measurement units, so they do store in their metadata information about the orientation of the camera, but it is not a requirement. The orientation can be computed from image alignment, but it cannot also. But if you have the orientation, it can speed the processing time. So this is something that it's good to consider if you're running a photogrammetry surface. Photogrammetry survey for scientific purposes. Now, camera calibration, knowing the intrinsic parameters of the camera as focal length, principal point, lens distortion is essential in photogrammetry. And a pre-calibration is not a requirement for most photogrammetry softwares, but these are done with the alignment of the images and from information in the metadata of the images. But having a pre-calibrated camera where calibration is done inside a controlled environment can aid the software with the alignment of the images. And at the Icelandic Institute of Natural History, we have a test field wooden grid with targets, which we use for pre-calibrating the cameras. So if you want to move from a relative model orientation to an absolute orientation of the models, then you have to use the GPS position of the camera. And drones do have that as well. They do store the coordinates of the images. But if you are working, for example, from manned aircraft, you have to find other ways of geotagging the images. And the more precise the coordinates, the more precise absolute orientation you will acquire for the models. So, and many drones, they do have RTK capabilities or PPK, where you achieve precisions of less than 5 centimeters for the images, and that also is resulting in very precise models, accurate models. Now, another thing that we do is we use ground control points, and these could be targets like this one, flags. They could also be not natural objects that are visible on the photographs, and these are then usually measured with a precise GNSS instrument, and then we can georeference the models very accurately using ground control points. And then finally, you need a workstation with good processing power, good memory performance, and graphic capabilities to process the 3D models and for feature extraction. The resulting products are then DMs and ortho images, and point clouds, and mesh models. Now, data acquisition, as I mentioned, can be done several means and ways. It could be through manned aircraft, satellite, helicopter, drones, on foot, from the sea, boat. So it doesn't matter really how you take the images. These can be used. We have mostly focused on or specialized, let's say, in manned aircraft photography using fixed wings, and I'll show you. We have used this 2-engine high-wing aircraft Partenabia TF BMW from Gardaflug. It's specially designed for photogrammetry surveys or science surveys in general, and it has a hole in the floor and can take cameras of different sizes and even multiple cameras at the same time. So it's a very good aircraft for photogrammetry surveys. And we have used this Hasselblad A6D camera, medium format, 100 megapixel, with a 35mm lens during the service that we fly with Gardaflug, and we have used this camera here in the Fagradalsfjall monitoring. We have also used other aircrafts like this high-wing 1-engine GF Klo from Flugfélag Austurlands. It has a big window, and that's another thing. We have to be able to open windows or the hole in the floor in order to place our cameras. And this one has a big window that we can use for oblique photography. And we have used a Nikon D850 45 megapixel camera for oblique photography. We have also used this high-wing 1-engine aircraft from the Ultralight Aircraft Association, Fisfélag Reykjavík, which has a hole in the floor, and we can position the Hasselblad camera actually in that floor, or other cameras in that hole, and picture vertically. And these are some of the tracks that we made flying in some of the surveys this summer and last year, presumably in the West Coast, is just to show how much coverage we can achieve in 1 3 to 4 hour flight. And we are collecting valuable data. It's extremely useful and good data that we collect from these surveys. And this is for oblique imagery only. Then we are focused more on outcrops for geological mapping. And this is the type of imagery that we collect, and you see there's a lot you can see in terms of geological mapping for stratigraphic correlations, mapping faults and dikes, or planning the field mapping campaigns. It helps a lot to have good imagery, good photographs, and especially if you can then create 3D models of these and do other types of measurements. That is very useful, and it saves you a lot of time and saves you a lot of money. These surveys are not expensive, but a field campaign where you hike and need to do the observations on ground, they can be very expensive. So you can save a lot of money by flying and extracting all the most fundamental foundational information beforehand, before you go to the field. And then of course it doesn't, you always have to do some field work to do the checking and map the rock types, but it can save a lot of time having good imagery for the planning. And these are examples of models, point clouds and a mesh model. Here of Herfell. And then these point clouds, these are areas, this is Herfell in Landafjörður, these are in the West Fjords. And you see we covered areas over 200 square kilometers in less than an hour. And these were used, actually, these models by experts working for Rammaáætlun, but they can also be used for geological mapping. As you see here, these are faults. You can draw the faults, and you can do measurements. You can measure strike and dip. You can measure bearing, thicknesses, and all that. And then you can draw vectorized lines, polylines, and draw them in 3D on top of these stereo images or mesh models, and then you can project them into profiles like this. And you see these are profiles that are 8 kilometers long, so but were probably photographed in less than 10 minutes maybe. So we are extracting a lot of data in a very time-effective way. And we also use drones for, let's say, close-range photogrammetry. If we're mapping outcrops or smaller areas, we have a fixed-wing EBX from SenseFlight, very powerful drone actually, and it takes images both vertical and oblique. Actually, the camera rotates, so and it can cover large areas in a short time. It has also RTK capabilities, so we get very precise models out of it, just straight out of the oven. Now, then there's a DJI Matrix 600 Pro. It's a tractor, I'd say. It's a very strong drone and can carry heavy cameras. So if we need really high resolution data, and we can mount our camera, the Nikon, the Hasselblad, under the Matrix and photographs. But yeah, especially outcrops, steep sides of mountains and quarries. But the most practical one are the small ones, and we used the Phantom 4 Pro. It's light. You can put it in a backpack and carry it and hike with it, and then fly. And you could use just any drone actually for this. But when it comes to photogeology, as I mentioned, these models, both mesh models and stereoscopic models, they are very useful. And we use two softwares for photogeology. One is called 3D Stereo Blend from Anchor Labs. It's a Danish company, and they work in close collaboration with GEOS, the Geological Survey of Denmark and Greenland. So they are geology focused, and the many tools within these softwares that are useful for geological observations and measurements. But we also are now starting to use Line virtual outcrops. These take the mesh models, and they also, there you can draw, you can overlap, you can put drawings on top of the models, cross sections, profiles. You can draw vectors and then export them as well. So it's a actually very good software. And the v3geo.com, it's a database of mesh models, and we have started putting some of our models there, and the models in actually Line, you can import models straight from v3geo. So it's very handy. These two work together very well. So if I just talk a little bit about the operation at Fagradalsfjall, monitoring there, we were requested to run the photogrammetry service at Fagradalsfjall, and we were doing so with Partinavia. Mostly, we also flew with Flugfélag Austurlands and with the ultralight aircraft, but we were flying to begin with almost daily, but then as it progressed on a weekly or 2-week basis, and or when weather allowed. That's one factor that it can be complicated here in Iceland, but we generated over 30 models of Fagradalsfjall throughout these 6 months of eruption. And the mesh models are available at Sketchfab. You can also go to the page of Náttúrufræðistofnun and find there all the mesh models. But we were achieving near real-time monitoring, which I think is a big achievement. We realized that it's a very time-efficient method. We could fly and do the survey in less than 1 hour, and the processing was then done in 3 to 5 hours. So we were actually delivering our data very quickly after the surveys. Actually, a low-resolution mesh model was delivered minutes after the images were processed, and then was sent to the civil protection and then to the media. And these mesh models were used for planning, safety, and other things. Now, it was a relatively safe monitoring. We could fly high above the air traffic. The level of exposure to danger was minimum because we were doing the flights in a very short time, less than an hour. So it was relatively safe. We also were quite away from the dangers of the volcanic eruption. We were covering very large areas, over 25 square kilometers in each survey, and we could cover much more. but it was, so the coverage was very wide. We were requiring good resolution of data between 7 and 30 centimeters in average, and we were also modeling the entire lava field. Sometimes, of course, areas need to be omitted where the plume was covering, but we could map the entire lava field, and that was, I think, what made this project so interesting. But the surveys yielded the information about volume, as you see here, area, and discharge rate. And the data, yeah, as I mentioned, was delivered to the civil protection within 3 to 5 hours. And the data is extremely interesting. We could, with the GMs that we were generating, we could create these, do the differencing, subtract one model from the other. And here, for example, when you subtract an eruption DM from a pre-eruption DM, then we get thickness models or thickness maps. And very interesting. And when you extract 2 eruption models, subsequent eruption models, then you get thickness change map. And then here you can see areas that are inflating or deflating or thickening, with stacking of lava flows and things like this. This is very important information when you are monitoring a lava field. There are many challenges of flying over an eruption like this. There's eruption plume, and depending on the day and nature of the activities, sometimes the eruption is very broad and wide, and there's turbulence, a boiling of hot air, and so planning the flight around an eruption is complicated. You have to actually mostly do it on site, and that is not easy when you also have to control the camera and think about the environment around you, or other airplanes and things like this. The cloud cover in Iceland, it's pretty bad, often low clouds. So these made it difficult for us to photograph and survey. If the clouds were very low, we had to fly low, and that meant more flight lines. And so the logistics of that were quite complicated. And then weather, wind, and other things. Then the loss of GCPs. We are in a very dynamic environment, and so many of the ground control points that we were placing, they were being overrun by the lava flows and destroyed and needed to be replaced. So we were regularly going out there to place new ground control points or targets. And one thing we didn't expect was, for example, this, brush fires or wildfires triggered by the burning lava flows, and also ejecta, ash, and hot bombs burning the moss and also burning our targets. So there were many challenges. Then air traffic also can be a problem, but we were usually flying high enough, so it wasn't that much of a problem. But it was, of course, a problem for photogrammetry service on ground with drones. Now we learned a lot from this experience, and there are things that we will be improving in the future. One thing that we were trying to implement was RTK, PPK positioning of the manned aircrafts. And here you see an experiment to add RTK, connect the RTK device to our camera. But yeah, there are some still complications that we're trying to overcome. But if we can get the position of our cameras very precise, then we will improve the models. Now, camera stabilization and gimbals. We're flying with small aircrafts, and there's lots of movement, especially in days where weather is difficult. And so having a camera stabilization that is specially designed for small format or medium format cameras, that will help. And yeah, have a flight management system that controls the triggering of the images, and also can help us plan the flights, these manned flights. Then that could also help and speed the processing of the data. We've also been surveying Surtsey since 2019, and published an article last year in the Surtsey Research. Erosion sedimentation Surtsey Island quantified from new DMs, and a model of Surtsey is already in V3Geo. You can actually access the site v3geo.com and see and find their model of Surtsey, and there you can do basic measurements. You can pan and zoom and look at the island from every angle, and then if you have access to Lime software, you can import the model into Lime and do other types of measurements. But it's also available on Sketchfab and on our webpage, on the webpage of the Icelandic Institute of Natural History, Náttúrufræðistofnun. But we've been generating high-resolution DMs and ortho images, and we can Joaquin. I want to mention this, that we have been working close collaboration with Landmælingar, Joaquin and Guðmundur Balsson have been actually key persons in checking our models and helping us with the geodetic surveys. So it's great that we can these institutes can work closely together. And Joaquin prepared two models, for example, from imagery from 67 and 74. And we've then prepared this model from 2019, and we have now a new one for 2021. But with these models, we can calculate the volume very accurately and area, and then compare. And do the differencing, for example. These are very interesting results for these two time periods, 67 to 74. We can quantify the coastal erosion and also how much sedimentation is taking place, and this information is extremely interesting. And now we have a new DTM for now high resolution DMs, 2019 one and the 2021, and I'll be presenting it, talking a little bit about it in a lecture in 2 weeks here at the Icelandic Institute of Natural History. But another thing that we do look at is is small scale 3D models, and we have, for example, been mapping footprints in Surtsey, and they are very well seen in the DMs. We generate these are we flew with a drone, but I also photographed just from the ground these footprints, and they have been now studied, and we're working on a publication about these footprints. Other things like specimens, animals, rock specimens can be photographed and modeled. This is also on our Sketchfab page, a model of the Great Auk geirfugli. You can look at it, look straight into its eyes, and so this, yeah, great arc is now accessible to the world through these models. So conclusions: photogrammetry takes geological terrains and outcrops into the lab to be mapped, measured, and quantified. The technique is cost and time effective. The monitoring of dynamic environments can be done in near real time, and the sky is the limit. Whatever that can be seen on an image can be mapped and quantified in 3D. I just want to thank your attention and thank you for participating in this lecture. All right.
Thank you so much, Birgir. I think if we have a couple of short questions, there will be time for that. We're a little bit over time, but if people are curious, I'm sure we can continue a bit longer. You can also, if you can either raise your hand, unmute yourself and ask it yourself, or ask a question in the chat. Yeah, Melissa, just on.
Hi. Hi, thank you so much. That was super interesting.
Hi.
Hi, I have two questions. Did you and Gro calculate the DDEM for the most recent Fagradalsfjall flight?
I haven't seen that. Gro maybe might know.
Joaquin calculated the differential map, yeah, from between the 30th of September and the 11th of November. Mm-hmm. And overall, we couldn't see anything, any specific changes. There are some cooling and contraction going on. Mm-hmm. And then there is some noise, but yeah, overall there was nothing really to be seen that was indicating change on the surface, at least significant changes on the surface, new flows or anything like that.
Okay, thanks. And my second question was, does it look like in 50 years there won't be very much of Surtsey left?
Yes, so the erosion of the lava field is pretty intense. So the Surtsey is composed of hyaloclastite mounds and also a lava field. So the south lava field kind of protects the hyaloclastite, but the lava field is eroding pretty quickly. And we calculated that maybe in 100 years, the lava field will be gone. But the hyaloclastites, which are actually pretty consolidated and hard, they might last for hundreds of years, I would say. But just like the other islands around Westman Islands. But yeah, we're talking about a few hundreds of years until Surtsey, is gone. But there's still some time.
Nice, thank you.
Any questions?
Austerroot wrote in the comments.
Oh, yeah, thanks for a great talk. Thank you. Thank you, Melissa, for keeping. I have my chat open over here on the other side of the screen. What are your future plans for the photogrammetry surveying?
Well, we are trying, of course, we have collected a lot of data now last year and this year, and we need to process this data. There's a lot of especially related to geological mapping, and we want to work on that. But the plan is, of course, to make this technology, develop the technology and work on improving, for example, these near real-time techniques and response. And so I hope, yes, to work in collaboration with good fellows from other institutions on this. But the possibilities are, as you saw, they're endless. There's so much that can be done, and people just have to be creative on how to use it. But at some point, we will need more persons working here for us, doing this full time, and certainly it's time consuming to process the data and work in the lab, and we are only a few here at the institute that do this, and so we hope we can grow and that this technology will be used more widely in other fields, and will serve as well also in geological mapping.
Thank you. Any other questions? I maybe have a short one. Are there any other cameras that you were thinking about purchasing that would open up new fields that you would be interested in addition to your RGB cameras? Is there something on? I know there was experiments with thermal cameras, but are there other cameras that you have thought, oh, this could be super interesting to do as well, or is it more the actual the FMS and getting the what do you call it? Yeah, the automatic triggering of the camera, etc. That will be the next technical developments at your lab.
Yeah, so I've been mostly with my RGB cameras, but we do have a small multispectral camera in our EBX drone, and we haven't used it much, but yeah, that's a possibility to use multispectral cameras, and definitely something that we could look into. But the thermal camera that we used the other day was very interesting, and I think we could also implement photogrammetry into thermal imagery, and I think that's going to be next on schedule when we monitor a volcanic eruption that we fly with two cameras, one RGB and then another thermal camera. And I think we already have seen that it's possible. We just, yeah, there's some few adjustments that we need to do with the thermal imaging, but it's possible. And then we collect incredible data actually by having these two, both the RGB and a thermal camera.
Okay, I don't see other people that have raised their hand, and I don't see anything in the chat booth. If you have raised your hand and I just for some reason cannot see it, just unmute yourself and ask your question now. All right, I take it as that I have not overlooked something. Then I just want to say thank you a lot, Birgir. It was an excellent talk covering a lot of things.
Well, thank you.
Thank you so much.
Have a good day.
Yeah, you too. And yeah, I will send an email where this link, there will be a link to this talk so it can be seen later if there's something you want to revisit. So, okay, bless.
Bye.